This is the 26th lecture. We continue our discussions on analog frequency transformations. Illustrate by an example, fairly involved example, and you must follow the steps carefully. And then we open the topic of digital filter structures. In the last lecture, we had talked about Chebyshev low pass filter design using for a given specification, and we illustrated with a couple of examples, and then we talked about the analog frequency transformations, and we showed that if capital S is the complex frequency variable of the normalized filter, in which the pass band with any tolerance delta p extends up to 1 radian per second, and the stop band starts somewhere at omega s with a tolerance of delta s. If this magnitude characteristics are described in the complex capital S domain, then this normalized low pass filter can be transformed to a denormalized high pass filter by substituting small s, capital S by omega p by small s. Okay. On the other hand, if it is simply denormalized low pass filter, where only the cutoff frequency changes, obviously capital S has to be replaced by small s divided by omega p, and then for denormalized band pass filter, capital S has to be replaced by s squared plus omega 0 squared multiplied by q divided by no omega 0. If you use q, yes?
Yes, sir.
Okay. Which I can write as s squared plus omega naught squared divided by bs, where capital B is the bandwidth. Okay. This bandwidth has the same tolerance as the normalized low pass filter. In other words, this 1 radian per second transforms to omega p1 and omega p2. So, the tolerances remain the same. Okay. On the other hand, if the if the transformation is to be from normalized low pass to denormalized band stop filter, then the transformation required is simply the reciprocal of the band pass transformation, Bs divided by s squared plus omega naught squared. The problem that arises here is, given a normalized low pass filter, you can always transform it, but suppose it is the reverse transformation, which is usually the case. The specifications will that be of either the band pass filter or the band stop filter. With denormalized low pass and denormalized high pass, there is no problem. The problem arises with band pass and band stop because of the constraint that they have to be geometrically symmetrical. In other words, omega p1, omega p2 is equal to omega naught squared. Usually omega naught is not specified. What is specified is the bandwidth omega p1 and omega p2, and therefore the product of them must also be equal to omega s1, omega s2. The stop band edges must also satisfy the same relationship. This geometric symmetry is inherent in the transformation, as I had showed in the last lecture, and therefore given specifications may not satisfy this. All that you have to satisfy is that omega p1, omega p2 should be equal to omega s1, omega s2. If this is not satisfied, then you have to adjust your stop band edges on either side, or if you so desire on both sides, so that the pass band specifications are met exactly and stop band either on either side is over satisfied. Okay. For example, if the specifications are this, let us say delta S, then delta P, this is 1, this is delta P. Let us consider a band pass filter, and the edges are omega P1, omega P2, omega S1 and omega S2. And suppose that omega S1, omega S2 is greater than omega P1, omega P2. Suppose it is greater, this is of course equal to omega naught square. Then what you have to do is, you have to make the left hand side smaller, and therefore you have to shift omega S2 to a lower value. Agreed? Omega S2 has to be shifted to, you understand why? You cannot touch omega S1, you cannot reduce omega S1, then the stop band specs will not be met. On the other hand, you can reduce omega S2, omega S2 you shift to omega S2 prime such that omega S2 prime is equal to omega naught square divided by omega S1. All right. Therefore, if you design this filter after this adjustment, the stop band on the right hand side will be over satisfied. The stop band on the left hand side shall be exactly satisfied. The pass band will be exactly satisfied. All right. This is the story if omega S1, omega S2 is greater than omega 0 squared. Now, if omega S1, omega S2 is less than that, case 2, if it is less than omega naught squared, then obviously you will have to increase omega S1. That is right. And therefore, what you have to do is omega S2 leave it intact, omega S1 you increase to omega S1 prime in such a manner that omega S1 prime is equal to omega S2 omega naught squared divided by omega S2. All right. This modification, although simple, has to be made, otherwise the filter shall not satisfy the specifications. We shall now take a fairly elaborate example to illustrate this. There is a further complication. After you have adjusted the edges of the stop band on the side depending on the situation, what is the normalized low pass filter? What are the specs on the normalized low pass filter corresponding to this? We know the tolerances, okay? Delta P in pass band, delta S in stop band. But what is the stop band edge? Omega S. That is also to be found out. Let's look at the example. I want you to follow this example in every step so that we don't miss anywhere. My specs are this. A fairly practical example. The magnitude is given versus frequency in kilohertz, not in radians, and the tolerance scheme is this. The pass band tolerance is 2 dB, this is 0 and this is minus 2, and the stop band tolerance is -50 decibels. minus 50, magnitude in decibel, and the figure is not to scale. The edges of the pass band are specified as 400 and 1200, and the edges of the stop band are specified as 100 and 3000. Okay, that is the specification. Now obviously you do not have to go to omega p1, omega p2, you can test with the frequency in kilohertz itself. F1, Fp1, Fp2 in this case is 48 multiplied by 10 to the power 4, whereas Fs1, Fs2 is equal to 30 multiplied by 10 to the power 4 kilohertz, I beg your pardon, yes, kilohertz square, that is the unit, correct. So Fs1, Fs2 is less than Fp1, Fp2. In other words, Fs1 has to be increased to Fs1 prime such that this has to be extended to some frequency where Fs1 prime shall be equal to 48 multiplied by 10 to the 4 divided by, yes, 3000, not 30,000, omega s2, Fs2, so many kilohertz, which is equal to 160 kilohertz, 160 kilohertz, okay. So this would go to 160. Now with these specs you have to design the filter, all right. The bandwidth is obviously 800 kilohertz, and therefore let us find the transformation. What is omega 0? Omega 0 is omega p1 omega p2 square root of that, right, and this would be twice pi multiplied by square root of 48 multiplied by 10 to the 4, and this comes out as, well, we need only omega 0 squared, isn't that right? We do not require omega 0, so why should we find that out? Omega 0 squared is 4 pi squared multiplied by 48 multiplied by 10 to the power 4, okay. And what do we require? We require the bandwidth B. B is 800 multiplied by twice pi, 2 pi into 800 multiplied by 10 to the power 3. So it is 1600 pi multiplied by 10 to the power 3. Therefore our transformation is capital S is equal to S, pardon me, B is in radians per second. We have to express it in radians because the transformation contains capital B, omega 0 divided by Q, that is in radians per second. Do not make a mistake. So it would be 1600 pi multiplied by 10 to the 3 small s, then s squared plus 4 pi squared multiplied by 48 multiplied by 10 to the power 4. All right.
So that also has to be converted into radians, 48 into 10 is 60.
We have already done so. Omega 0 squared. It has already been converted. Radian squared. Didn't we multiply the 48 times 10 to the 4 is kilohertz squared. Then I have multiplied by 4 pi squared.
So 48 into 10 is to 3
10 is to 3, it is in kilohertz also. First we have to convert it into hertz. Kilohertz. Yes. 10 is to 3 square.
Ah, okay, I made a mistake. FP1, FP2 is 48 times 10 to, this is in kilohertz.
Yes. So we have to convert it into hertz, then into radian.
Yeah. What about B?
B we have converted into hertz and then we have converted to radian.
So if I omit here 10 to the 3, it should be okay?
Yes.
Let's do that. So many kiloradians per second. Kiloradians per second. Is it okay now? No, it's not okay. Then small s should also be in kiloradians per second. We don't want that. In the transformation, small s must be in radians per second. So you must convert all of them into radians per second or radians per second whole squared. So this transformation is wrong. Okay, very good. What is the correct transformation then? Capital S equal to B we had converted to radians per second, that is 1600 pi multiplied by 10 to the 3. This is okay? Capital B. Only problem was about omega naught squared, that would be 4 pi squared multiplied by 48 multiplied by 10 to the power 10. With a little practice, you shall be able to avoid handling such large numbers. Okay? You could make this, for example, in hertz. The specification by frequency scaling, you could make that into hertz or divide by 100, so that your frequencies are 1.64 and so on and so forth, and then frequency denormalized. But that we will not enter into now, you do it yourself. So this is our transformation, and therefore our normalized low pass filter that we have to design should be like this. This should be 0 minus 2 magnitude in decibel, and the stop band at minus 50. This is 1 radian per second. What is omega s? That is the question. Omega s is what? You have to find that out. Find that out from where? What is your baseline? You can't argue that 1 is being converted to omega p1 and omega p2, therefore I shall multiply, I shall divide omega s1 or omega s2 by, no, that will not work. Okay? That will not, don't take a shortcut. You have to appeal to the basic relationship. What is the basic relationship? Capital S is equal to s squared plus omega naught squared divided by capital B S. This is the basic relationship, and we are trying to find out omega S. So if I put S equal to j omega S, all right, then on the right hand side we shall have B small s should be now j omega S1 or S2, j omega S1 or S2, because omega S corresponds to omega S1 omega S2. Is that right? The stop band edge of the normalized low pass filter will correspond to the two stop band edges of the denormalized band pass filter, and in the numerator I shall have omega S1 S2 squared minus plus omega 0 squared. All right. So omega S from this relationship shall be equal to, if we want only the two positive frequencies, okay, the two positive frequencies, then omega S1 squared shall be less than omega naught squared. Okay. So, we shall have to take in the numerator omega naught squared minus omega S1 squared divided by B omega S1 into no J. I am finding the real values, real positive frequencies.
Then there should be negative in the numerator.
So there should be negative in the numerator.
Doesn't matter. I have extracted the positive sign. This is not negative. I want a positive value of omega s,
Yes, sir.
right? So this is the positive value. The other value will correspond to minus omega s. All I need is a value of omega s, positive value. Is the point not clear? Ignore the j's. This becomes minus j. That's okay. But what do I want? Omega s, after all, in the normalized low pass, you have omega s and minus omega s. These translate to, these two translate to plus minus omega s1 plus minus omega s2. What we want to find out is a positive, the positive value of omega s. So I take the positive value of the transformation. The right hand side I take it such that omega s becomes positive. How does it become positive? Because omega s1 is less than omega 0. Now you might ask me,
It should instead be omega s2 square minus omega naught square.
Yes, sir, it should be that.
You should consider
Omega
omega s2 in
S2
this
square
case.
minus omega naught.
okay, I will take this also, this is another value divided by b
Omega s2.
omega s2.
So this is the positive value.
That is negative.
That is negative.
How can this be negative?
So because if we consider the j signs of omega s, that will be.
I told you j you ignore, because an imaginary frequency corresponds to an imaginary frequency. Okay?
Negative sign comes.
Doesn't matter. That will correspond to minus omega s1.
And it will be sir omega naught square plus omega s1 square. If we ignore the j sign completely.
It cannot be plus, because the relationship is this: omega naught squared minus either omega s1 squared or omega s2 squared. It cannot be a plus sign here, no. What is the confusion? Let us write it down. I must remove the confusion. Omega s is equal to minus b omega s1 or omega s2, not both, right, divided by omega naught squared minus omega s1 or omega s2 squared. Now obviously there are 4 possible values of this. Okay? Now what we want to do, you see, I took here j omega s. I could have taken minus j omega s. What would that have given? Plus minus this? Isn't that right? So, you see, I took s equal to j omega s, and that gave rise to this. If I had taken s equal to minus j omega s, then it would have given rise to same with a minus sign. I want to, there are 4 values now. I want to find out which ones are the positive values, because my aim is to find omega s. All I want to know, how should I design this normalized low pass filter? So I need a value of omega s. Whichever way you calculate, you will either find omega s or minus omega s. You can't find any other value. Now the positive value for omega s I can obtain in 2 ways. One is I take omega 0 squared minus omega s1 squared divided by b omega s1, or I take omega s2 squared minus omega naught squared divided by b omega s2. All right? These 2 obviously have to be identical. There is no other alternative, because they are the same value, they give the same value, they should give the same value of omega s. And is it difficult to see that this is equal to omega s2 minus omega S1 divided by B, because omega naught squared by omega S1, this is the adjusted value, omega naught squared by omega S1 is omega S2 and omega S1 squared by omega S1 is omega S1, and therefore, this is the stop bandwidth divided by the pass bandwidth. No, it is not quite correct to say it is a stop bandwidth. It is the difference between the two edge frequencies, stop band edges. That is, it is equal to omega S2 minus omega S1 divided by omega P2 minus omega P1, right. And this value also is the same. This is also omega S2 minus omega S1 divided by B. It is the same. They have to be the same, and this omega S has to be found out. It cannot be obtained by multiplication or denormalization of the frequency. This mistake has been propagated in many textbooks on analog as well as digital filter design. All right, take care of this. And therefore, in our case, omega S, the normalized analog low pass filter should have an omega S which is equal to the difference between these two stop band edges, that is 3000 minus what is our adjusted omega S1 on 60 divided by 1200 minus 400. So, this is 2840 divided by 800, or the numerical value 3.55. Okay. So, we are now comfortable. We have to design a low pass filter 1, 0, minus 2, 3.55 minus 50. Even classical textbooks on network design, filter design have made this mistake. They have not cared to find out what is omega S. Okay. So, my relationship is, now how do I proceed? My first thing that I have to do is to convert minus 2 dB as equivalent to, in terms of ratio, 10 to the power minus 2 by 10, that is minus 1 by 10, and this should be equal to, if I want a Chebyshev design for example, this should be equal to 1 by square root of 1 plus epsilon squared, and my calculation shows that epsilon is equal to 0.765. I do require epsilon squared also, and epsilon squared is equal to 0.585. Minus 50 dB in terms of ratio is equivalent to 10 to the power minus 50 by 20, which is 2.5, and the square of 10 to the minus 2.5 is 10 to the minus 5, and therefore, in order to find out the order, instead of using the cos inverse formula, let us use the basic formula, that is 1 by 1 plus epsilon squared Cn squared omega S divided by 1. So, Cn squared omega S should be less than or equal to delta S squared, okay, that is 10 to the power minus 5. Agreed? With a little practice you will be able to write this without the intermediate steps. Therefore, 1 plus 0.585 Cn squared 3. How much did you find out? 55 should be greater than or equal to 10 to the power 5. We can ignore this 1. We can ignore this 1 compared to 10 to the 5. Therefore, Cn of 3.55, if I take the square root of this and carry out the algebra, that comes out, I think I made a mistake here. I should have Cn squared 3.55 greater than equal to 10 to the power 5 divided by 0.585. And I am not sure about this calculation, please do verify. This should be greater than equal to, my calculation says 413.45. Is that reasonable? 2 point square of this, is it reasonable? Maybe I did it correctly. No? It's not?
Yes, sir.
It is reasonable. Okay. I had a doubt about this. Okay. So, if this is what is Cn, then we take some starting point and iterate. The starting point I took was n equal to 3. Then Cn of C3 of 3.55 would be 4x cubed, 4 multiplied by 3.55 cubed minus 3x, 3 times 3.55. Even if we take it as 4, 4 squared is 16, 4 cubed is 64, 64 multiplied by 4 does not make 400, does not come close to 400, and therefore n equal to 3 does not suffice. Take n equal to 4. N equal to 4, we have 8 x to the 4, that is 3.55 to the power 4 minus 8x square, C4 of 3.55 minus 8x square, that is 3.55 square plus 1, and this is 8 multiplied by 158.8 etc., and that suffices. Agreed? So, capital N equal to 4 is the answer. Fourth order Chebyshev low pass filter shall satisfy the specifications on the normalized low pass filter. What is the next step? Next step is to write down the low pass filter transfer function as a function of capital S, and that shall be since it is fourth order, we shall have two quadratics, S squared plus B1 omega p is 1, okay, B1S plus C1 omega p is 1, so C1 omega p squared, capital S squared plus B2S plus C2. In the numerator I shall have C1 C2, then divided by square root of 1 plus epsilon square. We shall have to do this normalization, and now you can calculate y2, no C0 has to be calculated, y2, then B1 C1 B2 C2, and then substitute in this and get the normalized low pass transfer function in the capital S domain. Finally, your band pass transfer function, the small s domain, shall be obtained by HLP capital S with capital S replaced by S squared plus omega naught squared divided by BS, and that is the end of the design. That is the transfer function. I made a mistake. No, that's correct. LP of capital S, yes, that is correct. Any question at this point? It's a fairly elaborate process, and you can make a mistake at almost every step. All right. Even very well known authors have made this mistake. Shlomo Karni, for example, I took this example from one of his examples and he has made a mistake. Okay. Mitra, I am not sure. You have to check whether he has found out the omega s correctly in the examples that he has taken. Similarly, you can design a band stop filter with arbitrary specifications. Our next topic would be digital filter structures. As I have talked about earlier, digital filters require only three basic blocks. One is the delay, which we denote by Z inverse. One is a scalar multiplication, and the third is addition or subtraction. And in order to respect the actual hardware process of addition or subtraction, we don't use more than two signals at any adder. Now, if you are given a structure, you can always analyze it to find the transfer function. The problem here is, given the transfer function, how do you find the structure? If you can find one, is this unique? No. Synthesis problems are always characterized by the fact that if one solution exists, there exists an indefinite number of solutions. Okay? But a solution may or may not exist to a synthesis problem. On the other hand, analysis problem, solution however complicated shall exist. Okay? We shall illustrate by two examples of analysis and then we shall go to the synthesis. If you are given a structure like this, x of n P0 summation, then there is a Z inverse. In the process, I shall also point out some of the disciplines that you have to observe. You must show the direction of signal flow. If an arrow is missing, your structure does not make any sense. So, Z inverse, and then you have a multiplier P1 that adds to summation, and this adds up to another. This is my yn, there is a Z inverse here, and there is a multiplier here which is minus D1. Suppose the problem is that of analyzing this structure. Well, that is rather easy. You can see that yn is equal to, it gets two signals, one is xn p0 xn, then x of n minus 1 multiplied by p1, so plus p1 x of n minus 1, then minus d1 y of n minus 1. So, it is a recursive structure because it requires a feedback, and therefore, I get yn plus d1 y of n minus 1 equal to p0 xn plus p1 x of n minus 1. And all that I have to do is now to take the Z transform of both sides, and the result is h of z is equal to y of z divided by x of z would be equal to p0 plus p1 z inverse divided by 1 plus d1 z inverse. Obviously, the structure that was asked to be analyzed is not canonic in delays. This is a first order filter and therefore should require only one delay. It should not require more than one delay. But it is canonic in multipliers. We have 3 coefficients and 3 multipliers. So, the structure that we analyzed is non-canonic in delays, but canonic in multipliers. We will show how to obtain a canonic structure a little later, but before that let us take another example. This is 6.5 from Mitra. We have capital X sub z adds to, draw this structure with me, two adders, and then we have a z inverse, and a feedback here with a multiplier K2. The other signal here comes from a multiplier minus K1, there is a Z inverse here from this direction, there is another summer, and this summer gets an input from this node minus K2. These two are connected, and then I have from here multiplier alpha 1, and from here a multiplier alpha 2, and this is the output. I must show this arrow, must show this arrow. Let us see where else. You must show the signal flow, even if it is redundant, even if it is obvious. You see, if I had not put this arrow, because I have indicated the output, the input is obvious. But even then, it's advisable that you show the arrows. Okay? Can I now proceed with the analysis? It is a fairly involved structure. All that I have to do is to find out what are the signals here and here in terms of capital X sub z. Okay? And it is a good idea, except at trivial nodes, to indicate some intermediate signals. We indicate this signal as W of z, this signal. There are many other ways of doing it, but I did it like this, and this signal I call this as V of z. That is enough. I do not have to indicate any other, because all other signals can be expressed in terms of W and capital V. And you notice that we can write W of z as equal to capital X of z minus V of z inverse K1. So, minus K1 Z inverse V of z plus, there is another signal here, this signal. So, it will be K2 Z inverse W of z. So, I have expressed W in terms of capital X, V and W. This you can take to the left hand side. So, W is expressed in terms of capital X and capital V. Now, capital V is very simple. Capital V of z is the result of addition of this signal and this signal. So, it is minus K2 plus Z inverse, there are two parallel paths, plus Z inverse W of z. And finally, Y of z is equal to what?
G inverse WZ
Z inverse WZ
into
alpha 2 plus
VZ
Z inverse
alpha 1
V Z alpha 1. Agreed? So, you have three relations, three unknowns Y, V and W. V and W you have already related. So, all that you have to do now is to eliminate W. And whatever way you do the algebra, you can verify whether I have done it rightly or wrongly. My calculation gives y of z divided by x of z, the transfer function, as alpha 2 minus alpha 1 k2 z inverse plus alpha 1 z to the minus 2 divided by 1 minus 1 plus k1 k2 z inverse plus k1 z to the minus 2. The job is done. I want to ask a question. What do you think, when will this be stable? Is it always stable? Not necessarily, it is a second order filter. What were the conditions of stability? This coefficient should be less than 1 mod, stable if, and what was the other condition? D2, is it the other way around? D1, mod D1 should be less than 1 plus D2, very good. Therefore, mod 1 plus K1 K2 should be less than 1 plus K1. All right. Can you make further simplification of this? Can you write this as mod 1 plus K1 mod K2 less than 1 plus K1? Can you cancel anything? No. No, you have to find out in the actual case what restriction does it put. But can you draw now a map similar to the stability triangle? We had drawn a stability triangle D1, D2 versus D1. Can you draw here K1 versus K2? Would it be a triangle? I don't know. You try it out. I have not tried. It's just a question arising at this point of time. Now, the other important thing in analysis and synthesis of digital filter structures is the so called delay free loop. And to illustrate this, I have taken another example. This is problem 6.1, where in some part of the digital filter structure you get a block diagram, you get a flow diagram like this. This is W of n, and then you have a feedback with D multiplier y of n, then C a summer, this is multiplied by B, this is V of n. I think I have reproduced it correctly. D, A, B, C. Okay. So he says the problem, I will state the problem later. But if you look at this loop, there is no delay in this loop. So whatever xn comes, it gets multiplied by A instantaneously, then by B, gets added to V, then by C, then by D, and goes back. And it will either increase or decrease the signal, and this occurs instantaneously, and therefore in no time the signal either builds up to infinity or goes down to 0. Okay? And such a loop cannot be implemented in practice. Okay, such a loop cannot, it doesn't make sense to implement this. You must have a delay. Delay free loops are unstable. You will either get nothing from the output or you will get infinite output. Okay, infinity of course you cannot get because your number of bits is limited, and therefore you will get a saturated arithmetic. There must be a delay somewhere. If by mistake such a delay free loop occurs in your realization, you can always avoid it by an equivalent structure. Here for example, you can write, there are various ways of doing this. You can write Wn as equal to a xn, Wn is a times xn plus c d Vn. All right, Vn c multiplied by d, and y of n as equal to c times
plus BCD WN.
BCD Vn multiplied by CD. CD, V is here.
So this WB,
Feedback loop from
Pardon me?
WBCD.
the previous equation.
Is
W1 into B will also
Oh, I am sorry. Wn
into B.
Plus BCD.
yes, BW minus BCD.
BWN plus
just a minute, let me make a check. Wn is xn a multiplied by whatever signal is here.
Yes.
What is this signal? Signal is, oh yeah, that's right. So it would be, I have written it wrongly. Wn would be equal to a times x of n is all right plus b Wn b c d Wn. Okay, that's fine. B c d Wn. In other words, you can write Wn in terms of only xn.
Plus CD.
plus CD into B.
So VN also.
Oh, why is things so complicated? Okay, C CD multiplied by Vn. Okay, fine. And then you can write the other equation, Yn, you can write as C times this signal, which is BWN plus Vn. Or you can write, no, you cannot write that, BWN plus Vn. Can you tell me what we said? Vn, Yn equal to C multiplied by
BWN plus
Vn. Okay. So what you do is you create, one of the equations was Wn 1 minus ABCD equal to AXN plus CD Vn.
So the bracket
A into
ACD.
ACD Vn. Okay. AXN plus ACD Vn, which I can write as A, alright, XN plus CD Vn.
divided by
Therefore, Wn is equal to A divided by 1 minus ABCD XN plus CD Vn. Okay, and if I want to construct this, then I simply Xn add to CD Vn, then multiply by A divided by 1 minus ABCD, and you get Wn. All right. Similarly, then you find out yn. Is this correct? Is this relation correct?
Yes, sir.
Yn equal to CBWN. So you have found out Wn, then you take B times this and add to Vn. Let me draw the diagram completely. What we have is x of n CD, this is Vn, multiplied by A divided by 1 minus ABCD, and this is Wn. Yn, in order to calculate Yn, I have to multiply Wn by B. Okay?
After summation.
Wn by, oh, there is a C. Okay. Let's multiply by B.
So we can multiply it after.
We can multiply it afterwards. Yes, this is what I was trying to do. You objected, so I got nervous. Vn also adds it, and then you multiply by C. This is y of n. Now you see in this diagram there is no loop, there is no delay free loop. Isn't that right? You have broken the loop. So whenever a loop occurs due to a mistake on your part, or somebody has given you the structure like that, then you break the loop by writing the equations and making sure that these equations are implemented without recursion. There is no recursion here, okay? There is no feedback loop without a delay. So delay free loops should be avoided. Now let's take the same transfer function. We made 2 points that given a structure we can always analyze it to obtain the transfer function. And then the second point is that the delay free loop should be avoided in any structure because they give rise to instability. Now we consider the question of canonic delay structure. You recall the first example that we took, P0 plus P1 Z inverse divided by 1 plus D1 Z inverse was delay non-canonic. In order to make it canonic, we represent this as P0 plus P1 Z inverse. H of Z is Y of Z divided by X of Z. So this is X of Z divided by 1 plus D1 Z inverse. Let's call this quantity as W of Z. Then this quantity I call W of Z. Then W of Z is equal to X of Z minus D1 Z inverse W of Z. Isn't that right? Is it okay?
Yes.
I have written it in a particular fashion. Now this can obviously be realized as X of Z summation. Then you have, if the output is W of Z, then you delay W of Z and then the delayed Z inverse WZ you multiply by minus D1 and add it here, then you get the output W of Z. Alright. To construct YZ, all you have to do is to multiply WZ by P0 and add it to WZ Z inverse multiplied by P1. WZ Z inverse is available here, so you multiply by P1 and add it here. This must be Y of Z. And you have used only one delay. Okay. This is delay as well as multiplier canonic. and this is the point that I stop.